Alcohols are an important organic functional group that you should know about. First thing we should know about is how to name them. Okay, now this first one, we have 3 carbons in it, and the alcohol, the OH group, is on the number 2 carbon. So we could name that 2-propanol, but my personal preference is to go propan-2-ol. Don't leave off the AN, it's a common mistake students make. On this bottom one we have 5 carbons, the OH group. Now if we were to count from the left, it would be number 5. If we were to count from the right, it would be number 1. So we number it to give the lowest number. So this is pentan-1-ol. Okay, you can call it 1-pentanol, that's okay too. This next one, we have 3 carbons in the longest chain here. We do have some side groups, and that's still going to be a propanol, propan-2-ol. We've got a methyl group off there, so it's going to be 2-methyl as well. Now you should be able to identify primary, secondary and tertiary carbons, remembering that the way this works is if you've got the carbon with the OH, this here, if that is attached to 1 carbon, it's going to be 1 carbon only, it's going to be primary. If it's got 2 carbons, it's going to be secondary. If it's 3, it's going to be tertiary. Okay, so when we look at this, this OH here, we've got this carbon which is attached to 2 others, that makes this one secondary. When we look at this OH here, and we see that this carbon here is attached to only 1 other, that makes this one primary. When we look at this carbon and OH here, it's 1, 2, 3 carbons, that makes that one tertiary. That's important to know. Okay, now the properties, you expect to know a little bit about that. So when we look at an alcohol, what kind of bonding is present? Well, for a start, as soon as you get any kind of molecule, obviously with temporary dipole bonding. Now because there's an O bonded to an H here, that means it's also going to have the ability to hydrogen bond as well, and that's probably the more significant factor. That means this will have a higher melting point and boiling point due to the fact that it can hydrogen bond. Now you're not expected to know compared to similar molecules that, for instance, amines, which also have the ability to hydrogen bond, although you would expect alcohols to be higher because of the electronegativity of the oxygen. More precisely, you're expected to make comparisons between, say, alkanes and alcohols. Now obviously alkanes can't hydrogen bond, so you'd expect alcohols to have a high boiling point. Carboxylic acids have the ability to do the dimers where it can have 2 bonds going on, so I'd expect them to be that, so it's going to be higher than alkanes, and that also means alkenes, haloalkanes because they can only have permanent dipoles, and also it would be higher than esters of a similar molecular weight, and aldehydes and ketones. It'd be higher than all of those, but they would be lower than carboxylic acids. Okay, it's kind of just being able to understand the difference in bonding there. Solubility. Well, because they have the ability to hydrogen bond, they can hydrogen bond with water, so they could be soluble up to 4 carbons, although butanol would probably struggle to dissolve. And obviously anything greater than 4 carbons, like pentanol and hexanol, won't be soluble because of the non-polar hydrocarbon chain. So that's the rest of the molecule we're talking about. So what do I mean by that? I mean this part of the molecule here is essentially non-polar. The difference in electronegativity between the carbon and hydrogen is fairly moderate, so that's non-polar. This does create a slightly, well, it does create a polarity, but once we get this large hydrocarbon chain here, well, it tends to nullify that, so that tends to dominate, so essentially the molecule becomes non-polar and therefore won't mix with water. Now, oxidation reactions, you should know from year 12 that this primary alcohol here, propan-1-ol, if you react it with dichromate, now remember specific conditions means things like being acidified, and obviously the name of the reagent, which is dichromate, or its formula. Now when it's oxidized, the first thing it turns into is actually an aldehyde called propanal. That's what that's supposed to be. Remember, if you look at this here, you notice there's just one H there, and this is very easily oxidized to propanoic acid. So depending if this was done in a flowchart, it could show this going straight to the carboxylic acid, or it could divide it up into two steps. If you have an awareness of that, it will make those easier, so you know that this could be shown in two stages, as it can be done like that. Now, you should mention or know the colour changes. Obviously dichromate's orange. I like remembering it in terms of the O for orange, even though I just did that in greeny colour, but anyway. And then the next one we're looking at is a secondary alcohol, and I've just chosen to use permanganate. Again, it's acidified, so I've put the H plus here, just to show you a different reagent, and that goes to a ketone called propanone. And in tertiary alcohols, I haven't drawn this out completely, they don't react. So generally speaking, if you're remembering these, and you just know that primary alcohols oxidize first to an aldehyde and then to an acid, and then secondary alcohols are oxidized to a ketone, that's really all there is to know about that. Okay. Now really this next one is substitution, and it's just really swapping out the OH group with a Cl, so it's substituting that. There's three reagents you can use. You don't usually use all three, you just use one at a time. SoCl2 is a favourite, and so this OH is going to get substituted. So on the other side, all you've got to do is write out, oops, I forgot to put an H there, the 4 carbons, and then throw in a Cl, and then just draw everything in, not just little sticks obviously like this, always remembering to put in H's, and that's a substitution reaction. Okay. Now one way of remembering this, you may remember SoCl2, PCl3, PCl5, and you may get confused what they react with. Obviously if they cannot react with a halogen, they're not going to substitute a Cl with another Cl. So remembering alcohol reactions, obviously, you know, it's just a way to kind of think about the reagent. Okay, just taking some time to consider what it could possibly react with and substitute. Now this is just an example. This OH here is obviously could get substituted, as could an OH if it was over here as well, and they would just get swapped out for a Cl. Okay, and that's substitution. It's called nucleophilic substitution because they like kind of nucleophiles, means attracted to a positive. Okay, they love them. Right, next one. Now again, you may remember elimination reactions from year 12. Elimination means something has been eliminated from the molecule, something's been removed, it's not being replaced. And the reagent we're here using is concentrated sulfuric acid. Now hopefully by the end of this course you'll start to remember that this is a dehydrating agent. It removes H2O. So we've got the OH here, then you have to choose an H either on this side or on this side. And this is where we get the possibility of major or minor products. And this is a little different from addition. Elimination is where the pore gets poorer. Now you wouldn't explain that in an exam that way. You'd say, now the H that's going to get removed is going to be the one which is attached to the carbon that has the least number of H's. So this one's got 2 H's, and this one's got 3 H's, and the one with the least is obviously this one here. So that means the double bond is most likely to form between these two. Okay, so when we draw that in, we're just going to draw a double bond there, and then we're just going to draw in the associated H's, taking care that we don't put any additional ones in around the double bond, which is all too easy to do. Now this isn't the only product, of course. These reactions happen very quickly. That's the major product. The minor product will be the one which has this H removed on this side. So when we're drawing that out, that's just going to be there. Okay, so it's going to have 2 there, and then we just finish with the H's. So you should be able to identify the two possible products. You should be able to describe what an elimination reaction is, where you get two atoms or groups, because the OH isn't a atom, it's a group being removed, and from the molecule with the formation of a double bond. Okay, so that single bond is no longer single, and that's elimination reactions, an important one to remember. Okay, and fifth one really is addition. Now this is how you can make an alcohol. Now we say dilute sulfuric acid. Sometimes that could be written as H2OH plus, and really all that means is we've put some acid into some water. So what we're really doing here is we're adding an OH and an H across the double bond. And again, we can get major or minor products, but this is to do with addition. So the OH, the H is going to get added to the carbon which has already got the most H's. So it's either going to go here or here across the double bond. Now obviously this carbon here has only got 1 and this has got 2 H's. So the H is going to go on this side for the major products. So if we go 1, 2, 3, 4, it's going to be H, and that means the next one's going to be OH, and we carry on and we draw in the rest of the H's. That would be the major product. So again, you should be able to explain how you decided on that, and that would be the H gets added to the carbon with the most H's. It's Markovnikov's rule, kind of the rich get richer. Now the minor product to that would obviously just be shifting the OH across, remembering these things are adding to the carbon which has got the double bond. So there's 2 carbons, this one and this one on the double bond, so we're not doing anything else. Oops, just take that out. To any of the other things, we're just concentrating around the double bond and then just drawing in the rest pretty much the same. Okay, so that's the addition reaction. So it's important to know the elimination and addition reaction, because they're kind of going back and forth between these two, between alkenes rather, and alcohols. Okay. Okay, now telling primary from secondary from tertiary alcohols can be awkward. In fact, students tend to always go towards the fact that primary alcohols can be oxidized, but so you'll see a color change with dichromate permanganate, but so will secondary alcohols. And often students will then get very complex in saying that primary alcohols get oxidized to a carboxylic acid, and you can test that with litmus paper. This is the test that you're really looking for to tell alcohols apart. Now the zinc chloride is a catalyst. The concentrated HCl, the Cl is what actually is reacting, and that's substituting across the substituting the OH rather. Now with primary alcohols there's no reaction, so it's going to stay colourless. Secondary alcohols are slow to react, and they take about 10 minutes, and they'll go to cloudy. Now the product they're forming is a haloalkane. Haloalkanes tend to be insoluble in water, and you'll see kind of a white solution because of that, due to the insolubility. And tertiary alcohols, very quick to react, well, relatively quick anyway, 1 to 2 minutes. Now just as an aside to this, we've seen that primary and secondary alcohols, you can also do this substitution reaction with SOCl2, PCl3, PCl5. And that's reasonably quick. Now, tertiary alcohols, you can also do a substitution reaction just by using concentrated hydrochloric acid. So, but the actual test for telling all three apart is this, okay? The Lucas reagent test. These are just, I just thought you should know some of the differences about why we have this SOCl2, PCl3, PCl5 reaction. you might be thinking, well, primary alcohols can't be substituted. They can, but we use a different reagent. Tertiary alcohols don't react so well with these reagents down here, so you can use concentrated hydrochloric acid to do that and change the conditions a bit. So that's just an aside. Okay, so that's alcohols. Okay, so to sum up, they can undergo oxidation, alcohols, or primary can go to aldehydes, then to carboxylic acids, secondary can go to ketones, and tertiary do nothing. And just a quick comparison with the Lucas reagent, that's kind of the opposite, using zinc chloride and conc HCl, it's colourless to cloudy. Tertiary are fast, secondary slow, and primary do nothing. So knowing the difference between those is important. And substitution reactions here, SOCl2, PCl3, PCl5, you're just swapping the OH group for a Cl group. Concentrated sulfuric acid, you're just removing an OH and H to form a double bond, so that's an important one. Addition reaction is kind of the reverse of that reaction. We have dilute sulfuric acid, you add it across a double bond, you add the OH and the H, and that makes an alcohol. So those are all the reactions.